Good morning. Thank you for joining us again on this beautiful Thursday morning. We look forward to presenting to you Street Lighting Design Basics 2.0. My name is Nadia Smith. I'm BEKA Schréder Senior Communications Officer. If you have any questions during the webinar, please type them into the question mark tab and we will answer them after the presentation. Please note that there are some brochures available for download in the handouts tab. And some of us are still presenting from home, so as always, please excuse any unusual noises in the background. Grant Combrink, our Marketing and Segment Development Manager, will give a brief introduction about the company, and then, and then Retief Kutzer, our Lead Design Coordinator, will present the Street Lighting Design Basics 2.0 to you. This will be followed by our Q&A session, and then finally, we will ask you to complete a short poll to give us feedback. I'm now handing over to Grant.
Morning, everybody. Thank you, Nadia. It's always good to remind us of where we come from. And what's important to that is starting with our Africa roots in 1978 to where we are now as a triple BE level 3 ISO certified local manufacturer, a manufacturer with about 300 plus staff complement. Also proudly part of the global Schder group, but we're not only a manufacturer of but also Luminance, and another service that we also provide to you is in-house lighting design and our R&D department. And you will notice in the next webinars to come that this picture will change slightly, and we will we'll be very happy to show you the changes that we are making within the organization, not only from a outdoor aesthetics look, which will be really nice to see in the up and coming webinars. So thank you. That was just a short little reminder for some of the new attendees of who we are, and let's go into some lighting design with Retief. Over to you.
Good morning. Thank you very much, Grant. Hello, ladies and gentlemen. Thank you very much for joining us today on this, as Nadia also said this morning, this beautiful Thursday morning. Today I'm going to be talking about Lighting Design Basics 2.0, specifically curves in the road. Obviously, our last webinar, we broadly discussed the basics of road lighting design. And today we'll be focusing on essential terminologies and metrics that are inherent to roads in the A class as per SANS 10098 Part 1. This is necessary just to understand when talking about A class roads, the metrics that make up an A class road. We'll then, by means of an example, do a short recap on Ulysses 3 that we did in the previous webinar. And finally, we will delve a little deeper into how to design for roads with curves or bends. I'll then summarize and I'll take questions. As you can see, we're going to go through the definitions, Ulysses 3 recap, lighting of curves, and the summary. All right, going into the next slide. I think most of the audience here might be familiar with this table in SANS 10098 Part 1. But for those who aren't familiar with this type of design, I think it's necessary to simply go over the metrics that form the A-class definition. And you'll see that there are typically 4 metrics: minimum average luminance, the candela per square meter, overall uniformity or overall luminance uniformity, longitudinal luminance uniformity, and then finally threshold increment. Sorry, I'm just moving something out of my way on my screen. In the next few slides, I'll try to clarify a little what these represent. For those who know, this will be a little bit of a refresher. For those who aren't familiar, this might be some good information to learn. Right. Okay, so the first metric we come to is average luminance, or LN, marked by LN. This is the mean luminance over a specified section of carriageway viewed from a specified observer position. Average luminance is the mean luminance over a specified section of carriageway, and it's viewed from that that observer position that's 60 meters in front of the first transverse row of calculation points and 1.5 meters above ground level. The field of calculation should cover a section of road between two luminaires in the same row. And for average luminance, the position of the observer must be at 1/4 of the carriageway width from the left-hand side of the road when you're driving on the left. The next metric is overall luminance. As I said, sorry, just to recap, I'm quickly going through the metrics so that we can understand A-class roads and then delve into how to design for curves of a road. All right, so the next metric is overall uniformity. And overall uniformity, this is the ratio of the minimum calculated luminance value to the average calculated luminance value. The observation position must be at 1/4 of the carriageway width from the left-hand side of the road as for luminance. And I've noticed over time that some people do struggle with the understanding what overall luminance uniformity is. So I've gone and I've created an image to kind of indicate what uniformity is, overall uniformity at least. As you can see in this image, I've created those two identical areas with the exact same luminaire, placed at the exact same mounting height, and in the center of each of the areas. These areas are exactly the same length and width, and the luminaires are at exactly the same mounting height. The only difference here is the optic that I've used, where the area with bad uniformity on the left has a luminaire using a narrow beam, and the area to the right has a luminaire using a wide beam. And it's quite easy to see that the area with good uniformity has a much smaller difference between the minimum value of 49 lux and the mean value of 142 lux, giving an overall uniformity of 34%, compared to the area with bad uniformity with a value of 7%. Now, those values are, as you can see, top left and top right on the image. I've then created a pseudo intensity image just to show that in this image I simply want to highlight through use of a pseudo intensity color the spread or distribution of the flux incident on the two surfaces. It's quite clear in this image that there is a major gap between the minimum lux value and the average lux value in the leftmost image, whereas the gap that has significantly reduced, whereas that same gap, sorry, has significantly reduced in the image to the right. So you can see on the left, you've got a really bright hotspot, if you like, with very high maximums, and to the corners you can see the very low minimum. So that ratio is quite high. But then if you go to the image on the right, although the average illuminance has reduced a little, about 60 lux average, you've got a much more uniform spread of illumination. And for the person viewing the luminance as they drive, it's very important to have good overall uniformity. The next metric is longitudinal luminance uniformity. We need to understand longitudinal uniformity. This is actually a very important form of uniformity. This will be calculated for the center line of each lane, and is the ratio of the minimum value to the maximum value, with the observer placed in the center of each lane at 1.5 meters above the road, facing the direction of travel, measuring the minimum and the maximum value, and expressing it as a percentage difference. I found this image online, which is just a nice little image to show the observer and where longitudinal uniformity is measured. So this, obviously, you can see the observer where the vehicle is facing the direction of travel. You measure in that center lane, in the center of that lane, the minimum value and the maximum value, and you then determine your longitudinal uniformity. Why do we do this? This image, well, we do this because we need to minimize the zebra effect. All right. The zebra effect is repeated bright and dark regions on the whole road surface, which may cause strong psychological and visual disturbances to drivers, which can become dangerous in the sense that it can cause visual fatigue, your eye having to consistently make thousands and thousands of adjustments to adjust your visual acuity. And also some say this can cause type of hypnosis. All of this is dangerous to the road user, to all stakeholders, obviously, on the road. So it's very important to have a good overall uniformity and a good longitudinal uniformity. And you'll always notice in A-class roads that the longitudinal uniformity is higher. The requirement for the uniformity for longitudinal uniformity is higher than that of overall uniformity. And this is, again, purely for that visual comfort aspect, to make sure that we provide an environment where you can see comfortably and without any undue strain in the whole visual process. Okay, then the final metric that we look at for A-class roads is your threshold increment. Now, the description on SANS 10098 Part 1, it says the percentage increase in contrast required between an object and its background for the object to be seen equally well with a source of disability glare present. Now, the threshold increment, or TI, is expressed as the difference between the value of the threshold under glare conditions and the same value without glare, expressed as a percentage of the value without glare. I've tried to find an image that really represents what is being said here, because I know sometimes language becomes confusing. And I know when I started in lighting, this was something that I really struggled with. But I think I found something that might help. And in this image, you can see in the images left and center, we can see the sources of glare in a pseudo intensity view along the road. Now, in the image to the right, I've tried to indicate the object to be seen with a source of glare present. You'll notice that due to a large difference in contrast between the source of glare and the object to be seen, we cannot see into that area at all. There's no way we can see what's happening there. Also, this image shows a little bit clearer the effect of veiling luminance, which is a luminance superimposed over the eye's retinal image produced by stray light within the eye. The word veiling luminance kind of gives you a good verbal understanding of what that light does. If you, my mentor, Mr. Marie Cronier, always said it's like the bride's veil. The light being emitted out of the luminaire creates a kind of veil over the retina, over your eye, over your perception, and you have to look through that to try and see. And this is why it's important to take TI into account as well, and that's why the standard allows for a threshold increment. Okay, now we've gone through the metrics. We're going to now start on the recap through an example of Ulysses and what it can do, and then how to determine spacing on a road. So now that we've refreshed our understanding of the metrics used for A-class roads, we'll, through use of this example, also recap on the use of Ulysses 3 in optimizing street and road lighting designs. In this image, you'll see two generally straight sections of road, obviously the picture north and the picture south, and we'll there's a pronounced curve to the left of the picture. But first, sorry guys, just to let you know, I went and looked for the curviest road I could find, and I thought Lesotho is a really good mountainy, hilly country, and that's why I've used this as an example. And we're going to assume this is an A-type road. Obviously, this isn't an A-type road. In reality, this would be a B-type road or street. But for the purpose of this exercise, we're assuming this is an A-type road, and that we're going to also allow for that curve or bend in the road. All right, so first we need to calculate the best spacing at the lowest mounting height using the least power in order to achieve the required class of lighting as per the standard. And we will then need to allow for the curve also as per the standard 10098 part 1. Okay, so first, as a recap of Ulysses 3, you will agree that we first need to know the carriageway dimensions and class before we can get started. Here I've measured the section of road representative of the average geometry of the general roadway to be designed for. You can see that to the bottom left of the picture, where you can see 7.5 to 8 meters. We can then use Ulysses 3 to create a cross-section of this road and start determining the optimal lighting solution. Optimal being best spacing, lowest mounting height, lowest power consumption, most optimal use of optical control in order to get the further spacing for this installation. I then assumed a class of A3, no median, 300, as per SANS 10098 part 1, and I've applied a reflectance factor of R3007, which is slightly specular new asphalt on the paved road. We then need to place the pole and luminaire in the correct positions as per the client's request regarding mounting height, setback of pole, outreach of outreach arm, rake angle, and finally the luminaire to be used. In this case, we used the new LED Lumidi XP range of luminaires that the BEKA Schréder have recently launched. And finally, we can now calculate the optimal solution. Now you can see, just get my laser pointer. When one of the best features of Ulysses is that we can basically create any kind of road cross section. In this image to the right in the center, you'll see that we've created 2 lanes of 3.75 each, which is basically the half of 7.5. I've given it a name of Lesotho Curved Road, A3 no median 300. We've placed our pole. When in Ulysses 3, you have 2 sections where you can populate the information necessary to create the road cross section. The top section here is for the roadway or the carriageway, and we can see that I've given it its name here, which then appears at the bottom of this image. You can change all the colors if you like of the asphalt. It's a car, it's driving left. There's 2 lanes, 3.75 meters each. It's a luminance calculation with the surface of R3007. We're using the CIE 140 method of calculation for the South African A3 no median 300 standard of for this roadway. Then we need to go and tell Ulysses what luminaires to try, and this is where it's such a brilliant program. We can give it a height. Sorry, as a rule of thumb, the height of the pole is generally the width of the road. It might sometimes be a little bit higher than the width of the road, or a little bit lower in the width than the width of the road. But rule of thumb, if you're not too sure what mounting height to install on a new road, if your road is 8 meters wide, for instance, you can start looking at an 8 meter high mounting height, maybe 9, maybe 7. With LED technology, generally we can also go lower than the width, but that's your rule of thumb. All right, but in this installation, we're using an 8 meter mounting height, and we can decide the iterations to test. So I started at 30 meters, and I said I'd like to go all the way up to 60 meters, testing at 1 meter intervals, using a luminaire at 0 degree rake and at 15 degree rake. In iterations of 15 degrees. So this means Ulysses will now test every luminaire I've specified to test in this installation at 30 meters, 31 meters, all the way to 60 at increments of 0 and 15. And it does this super fast. You can see I've got 8 fixtures defined, and then my setback here you can see is 1.5 meter setback with a 1 meter, an overhang of -1, which means it's actually got a very short spigot, and there's 1 meter between the luminaire and the curve or the yellow line. And that's a really good feature of Ulysses. You click the result and you come up with your optimal solution. And just get rid of the laser. Okay, once we've done that, get my laser, we come up with the optimal solution in the range of luminaires that we've chosen. Here you can see that we have a compliant result going from left to right, you've got all your different values that you need to look at. So you've got a compliant result at 42 meter spacing with the setback as indicated, 1.5 meters with a spigot or a 150 mil spigot, 15-degree rake. Here you can see 15-degree rake. And we're achieving, this is what you should be achieving. And this is what it's being, and this is what's calculated. So this is what it's measuring it against. And you can see that we're achieving 0.75 candela square meter. Overall uniformity of 50%, which is very good. Longitudinal uniformity of 57%, which is good. Longitudinal uniformity of 65% in the second lane, which is very good. And then a TI of 19.8. And I'm going to explain that sometimes we have to do a trade-off for performance and comfort. So here we can see that the optimal solution was the LEDLUM MIDI XP 88 watt 5307 optic at 8 meters height mounting with a 15-degree rake, 42 meter spacing. The values we've achieved are all compliant to the standard. In this case, you will notice a threshold increment that is close to the threshold. And this is sometimes the case where there is a balance to be maintained between cost of installation and product, where budget is an issue and performance or comfort. So the LEDLUM XP range lends itself very well to those installations where budget is a constraint, but performance and reliability is a must. In any case, we now know the optimal spacing for this section of straight road. So you see, in many cases, the client might tell us, listen, we have a budget constraint, but we do need to achieve compliant results. Then we have a range of luminaires for this, and here you can see how the XP range lends itself well to the performance of being compliant and achieving maximum spacing, but it doesn't necessarily, in this instance, reduce the TI to a far lower value, which is something that in cities you would like to see. This is not a city road or a major urban environment. Okay, so we've now got our 42 meter spacing, but what about the curve? We can't apply a 42 meter spacing to such a hairpin curve. It's just not it's not good practice. We'll have major dark sections. So, sorry, I just get rid of my laser. We have to go and work out the curve spacing ratio. Sorry, I do that often. So as you can see in the excerpt in this image of SANS 10098 part 1, it stated that where lighting is to be designed for curves in a road, spacings between luminaires will have to be reduced in accordance with the radius of curvature and the installation positions of the poles. In other words, on the inside or outside of the curve. Details of recommended spacing on curves are given in Appendix C. That is Appendix C. This I'm going to explain a little bit later for those who don't know, and it might just be a refresher for those who do. But first, obviously, we need to determine the curve radius of the road so that we can start using Appendix C. In order to figure out the curve of the radius of the curve, you'll see in the bottom right, the image to the bottom right, the width of the arc and the height of the arc is now shown. And for us to determine the radius, we now need to apply the formula shown. So here you can see the formula we use is height divided by 2 plus width squared over 8 times height. Where, let me get my laser, where height, which is this bit here, and I've just zoomed in on that area here, is 48.541 meters divided by 2 as per that area there, and that equals 24.2705 meters. Then where width squared is the width, which is that area there, we square that and we divide that by 8 times 48.541, which is 8 times 8 times this height. So we get to 24.2705 plus 15,189.08 meters. divided by 388.328 meters, which is 8 times 48.541. And we get 24.2705 plus 39.114 meters, which is approximately 63.38 meter radius. So now we know that if this was a circle, the radius would be about 63.38 meters to that arc. But what do we do with that information? How do we take that radius and determine the curve spacing ratio on this curve? Well, pardon me. Get rid of my mouse. There we go. We now use Appendix C. We can take. We need to take the calculated radius and apply it to Appendix C in order to determine the curve spacing ratio. On the x-axis, which is the horizontal axis going from left to right at the bottom, we can see each vertical line representing a 100-meter radius interval, and on the y-axis, which is the vertical axis to the left, we can see each horizontal line indicating a factor by which we will multiply the calculated optimal spacing in order to determine the spacing on a curve or bend in the road. The yellow line, I've made it yellow. It's not yellow in the standard, obviously. The yellow line indicates the factor to be applied for luminaires placed on the outside of the road. And the green line, again, it's not green in the standard, it's black, indicates the factor to be applied for luminaires placed on the inside of the road. First, let's find where to start using our radius of 63.38 meters. All right, so you'll notice that at the bottom left, the x-axis starts at 100-meter radius, which means we can't go further, we can't go lower than that. That is our minimum. That's where we'll start with our small 63.38 meter radius. It's a very tight curve, which means we're probably going to have a reasonable reduction in spacing on the curve. So this is how we will do it. We need to zoom in and figure out what the iterations are between the 0.6 and 0.4, and we can easily see that we need to subdivide the major y-axis horizontal lines. We see that they are subdivided in increments of 0.4. But the yellow line is denoting luminaires placed on the outside of the road. It's not one of the major y-axis increments, but rather falls in the minor y-axis lines. So we now need to subdivide the 0.6 to whatever that line above it might be. So we'll go into the next slide. Now we can subdivide that, and we figure out that it's we then must break that down again into smaller constituents and find that if divided by 5 we get increments of 0.008. From here it's rather easy to see that the factor that we will multiply our optimal spacing with is 0.632. Once we've multiplied the optimal spacing with the curve spacing ratio reduction factor, we can see that we need to apply a spacing on the curve of the road of about 26.5 meters between poles in order to allow for safe visual driving conditions in hours of darkness as per the standard. And now we can comfortably take this information and start plotting our results. So you can see, get my laser. So you can see that we've taken that original curve radius. We've found it on the y-axis and the x-axis. We know that we want to be on the yellow line, which is for luminaires placed on the outside of the road, and we need to figure out what that factor there will be. And then once we zoom in on that area, we can see that with increments of 0.008, we can figure out that it's we can safely say that it is a factor of 0.632 times 42, giving us 26.544 meter spacing, which we then obviously round down to 26.5 meters between poles. Okay, get rid of this. Moving on to the next slide. All right. Now we have our results for an optimal spaced straight section of road, as I've shown. To the south of this picture and to the north of this picture, we have generally straight sections of road. And then to the far left, we have this very pronounced curve that we need to apply this factor, this spacing, curve spacing ratio to. Here you can see that we take the results from Ulysses, which is a 42-meter spacing between poles with that specific luminaire on this section of straight road, and we'll do the same here to this section of straight road, exiting, if you like, the curve. So here it starts and here it finishes. But on the curve itself, we can now apply that curve spacing ratio and apply it at the increments that we've measured, 26.5 meters, and then carry on. Why is this important? Well, if I'm just going back one slide, it's important because now we can safely give or provide the client with an accurate bill of quantities for the luminaires as we go along the road, having reduced the spacing on the curve to provide for a safe driving environment and hours of darkness, and then going back. So if this was the total project area, the total extent of the design to be designed for, we can now give an accurate and safe design to the client, where if you do not do this, you're actually endangering people's lives who are entering this bend, those who are driving, and also potentially those who might have been living on the edge of this curve, where you might have lost, where they might lose control, or whatever could happen. You know, we need to make sure that we always, when doing a lighting design, we provide the safest possible results. Okay, we've gone through this. Once you've calculated, you can now actually quite clearly see the effect it has on the road. What I did here was I took the the values from Ulysses, and I took the curve reduction factor. I then opened my AGI, this lighting design software, and a Google Earth image that you've seen just go back to that slide, which was this Google Earth image. And I've cut out, using AGI, I've cut out this section. I've created a solid surface, a solid planar surface, and I've cut out this section as a road, and I've applied this as a road contributing surface. So this is, in fact, when you see the calculated result, you're actually seeing what it would look like on an R3007 surface visually. So this is what it would look like from a plan view, and you can quite clearly see that the bend is now very well illuminated, going into and exiting the bend. When sometimes it's easier to see it in 3 dimensions, so I've just taken an isometric view of that curve, and you can see it's very well lit. This is paramount to the safety of all the road users, all the drivers. I've also indicated the installation in a pseudo intensity image, so that you can see the average on the straight sections of road, and then how it increases on the bend as per the standard. And again, there's an isometric view here to show how that's increased. You can see we're achieving areas of 1.1 to 1.5 candelas per square meter. In fact, in the red areas, the red indicates a minimum of 1.5 candela per square meter and higher. And that's the bare essentials of designing for curves in the road. Okay, so as a summary, I've gone through the definitions of A roads, looking at luminance, overall uniformity, longitudinal uniformity, and threshold increment. Ulysses 3 recap using this example for a road specific example. We need to identify the road that we're going to calculate for. We need to understand what needs to happen there. This is normally information that the client provides us. We have to then create a cross section in Ulysses. so that we can produce a valuable lighting design, and then optimize so that we provide the client with the most cost-effective and the best solution possible before we plot. And then using the lighting, the Appendix C, we can then accurately design and figure out the reduction factor on curves for specific roads. And then once we've done that, I hope this was an informative session where we could help those who already knew how to implement this curve spacing ratio, have a bit of a refresher, and also assist those who didn't know to gain a bit more knowledge on another part of the dynamics of street lighting design. Thank you for the opportunity. I'll now hand over to Nadia for any questions. Thank you, Nadia.
Thanks, Latif. Okay, so as you've heard, it's time for the Q&A session. So just a little reminder, if you do have any questions, please type them into the question mark tab. We do have some comments and questions already. So here's the first comment. 0.34 for minimum average should not be considered a good uniformity, rather state improved uniformity. 0.4 to 0.5 uniformity would be good, and 0.7 to 0.9 excellent uniformity. I don't know if you want to
agree
comment.
with that. I was purely showing. No, that's fine. I agree with that statement. I see how that can be confusing. I agree. In road lighting, 40% would be the bare minimum overall, minimum maintained overall uniformity. But for the purpose of this exercise, my intent was to purely show the difference between bad and good uniformity, or bad and better uniformity. But I fully agree with that statement.
Thanks, Latif. Then here's a question. Is the TI not a mandatory requirement under the standard, thus determining the minimum value to achieve?
It is definitely a requirement. It is you have to allow for TI. You cannot go over the threshold as indicated. So in an A class, the highest A class, you'll have a TI threshold of 15. You cannot go above 15%, and the lowest is 25%.
Okay, thank you. Here's the next one. Considering road curvature lighting Appendix C, how would one light a large traffic circle of 100-meter diameter, 2 lanes of 3.7 meters each, and solid garden island? There are also 5 arterial roads equidistant.
No, you do not use curve spacing ratio for that type of design. This is a completely different type of road lighting design, which we'll hopefully get a webinar on, but you'll not use curve spacing ratio. This SANS 10098 Part 2 talks about specific sections and types of road, which includes toll gates, which includes intersections and T-junctions. You will not, curve spacing ratio is purely for long stretches of road that might have bends in them. That is purely for a bend in a road, but not for an area on a road where you're going to have much traffic, like a circle or a crossroads or a T-junction. This is a completely different design.
Thanks, Latif. Then on the curve spacing ratio, what is the minimum radius for one to apply this reduction factor?
100. If I may, let me just go back to the presentation. Get my laser pointer. This is the minimum radius. This here shows the minimum. So even if you had a hairpin bend coming right back on itself, this is what you would apply. Obviously, there is no such bend, but this is the curve space, the minimum curve spacing ratio you start at, and then determine the factor for luminaires on the outside or on the inside or on the outside, the way I've showed you in the presentation.
Okay, then the next question, does the tilt increase TI?
It's generally it would, but it's again, that's it's dependent on the design of the optical control. So some optics are designed to be tilted or designed to be raked so that you can have a lot of flux thrown across the road, specifically in wide roads, but we still need to reduce the TI, the glare, make sure. So that there's a lot of work that goes into the design of these optics. Also, generally, the TI is also affected by the maximum intensity area on the photometric web, where that maximum intensity lies on how the flux is emitted from the luminaire. But as a simple answer, if you're going to increase the rake, you're going to see more of the flash area or the luminous opening. So yes, glare will potentially increase, but that's why when we design, we make sure that it's all within the standards and it's all compliant.
Thanks, Retief. Is there any design booklet available for this?
A design booklet? I'm not too sure. What do you mean? A design booklet?
I think a booklet with, you know, the way I understand it, with instructions on how to design. That's how I understand it.
If there is, I'm not too sure whether there's a design booklet on it. I know AISA does very good courses on road lighting, which is something I would attend if that's a good answer. So definitely get in touch with AISA. There's also lots of content available online to learn, but the best is to obviously approach a reputable company who have a lot of experience in this and attend webinars like this, because you can take the slides and apply it to your design. But if there's a booklet or not, I'm not too sure. Unless you buy the, I think the IS lighting handbook, it's quite expensive, but that is a font of knowledge.
Okay, then what curve ratio do you use when the fitting is mounted on the median and not on the outside or inside of the curve?
It's a good question. I don't think I've ever had that. Yes. So the way I understand the question is, what curve spacing ratio would you apply if the luminaires are placed on a median and not on the outside or inside of the road? If I had to logically consider this, it would probably be the worst case. So that would be if wherever the tightest radius is, in my opinion. So if the tightest radius is on the inside, I would use that radius to determine the spacing ratio, just to be conservative in our reduction and make sure that we rather overcompensate than undercompensate for the curve. I hope that answer makes sense. To me, to summarize what I've just said is, if there's luminaires on a median and you have 2 lanes on the outside of the median and 2 lanes on the inside of the median, I would potentially use the the radius of the curve for the inner 2 lanes rather than the outer 2 lanes, as these would be the more this would be the tighter bend, and would probably need well, it would be the determining factor for the curve spacing ratio. but I'll do some research.
Thanks, Retief. Then we have, when calculating spacing, what did you multiply the spacing ratio with?
When calculating spacing, what did I multiply the spacing ratio with? Oh, I multiplied it with the optimal spacing calculated in Ulysses. Let me just go back to that slide. If you can see in this slide, I've created, we found after we've input or populated all the parameters to be calculated for, I calculated that 42 meters was the best spacing we could achieve with any of the family that I put in as a reference, and we can see that 42 meter spacing between poles on a straight road was the optimal spacing. I then multiplied that by the curve spacing ratio, which we calculated to be 0.632. So once you calculate 42 meter optimal spacing with 0.632, which is the curve spacing ratio we calculate using Appendix C, we can see we achieve a curve spacing ratio or a curve spacing of 26.5 meters. I hope that answers that question.
Thanks, Retief. Can one use the Relux software to simulate street lighting design? Sometime back we were advised otherwise.
I don't know who advised it, but I'm sure you can. We don't work in Relux often. In fact, we trust our Ulysses 3 software. It's been third-party verified by Laborelec in Belgium. But you can, yes, definitely. Relux has a very good module on street lighting, and you can definitely do street lighting in Relux. Absolutely, I don't know why it would be advised not to.
Okay, then we have some questions here about roundabouts, but we will look into that for possible future webinar to have a separate session on that.
Yes.
Let me see. Here's the next one. With improved optics, would one not be able to improve on Appendix C spacing table? The example seemed over-designed.
I don't know. There are people much smarter than I that should answer that question. You said would one? What was the? I just want to make sure I understand the question.
With improved optics, would one not be able to improve on Appendix C spacing table? The example seemed over-designed.
Okay, so the way I understand this question is that the spacing table needs to be improved on. But that's for the CIE to determine. I can't determine that. How if that's what's being meant by the question. However, if what's being meant is, can't we change the optics to have a bit of a bigger spacing on the curve because it seems over-designed, then potentially, yes. I can't see why not. In this case, like I said, we've used the best optic in this family, in the XP family, but were I to use, for instance, the LED Lume family, which has a bigger range of optics, we could potentially get a better spacing. But remember, the spacing is not let's start again at the optimal spacing on straight roads. That's what's going to determine the spacing on the curve. So if on the straight road we want to achieve a spacing of say 50 meters between poles, yes, then if I see, okay, my XP range is not complying to this, but budget is still a constraint, I might move on to the LED Lume MIDI range, not the MIDI XP range. where I have a few more optics to choose from, and these optics are being developed continuously. So yes, it's possible, if I'm understanding the question correctly in that way, that we can increase the spacing on the straight road, and then we'll always get the same curve reduction spacing ratio on Appendix C, but that will just mean we've now got a bit of a bigger spacing between poles, because we had a longer spacing or a wider spacing between poles on the optimal straight section. But if the question is regarding the table itself, I can't answer that, unfortunately. I'll try and find out whether someone will be able to change the table. Did I answer the question correctly? Is that okay?
Yes, Latifia, you can carry on.
Okay.
Okay.
So that's my answer.
Then we have a comment still about the design booklet. So someone commented to say that the design booklet would be SANS 10098, as it provides recommended design guidelines to start with prior to courses, etc. Okay, then I actually can't see any further questions
Roger,
at this
yes,
point.
Hold on, I can see one. Someone is asking ISA. Sorry, ISA. When I said ISA, I meant Illuminating Engineering Society of South Africa, ISA.
Okay, thank you. Okay. I think we have another comment. Sorry. I would not recommend the amendment of the spacing table as it is related to road lighting levels and line of sight.
I agree.
Okay, good. Then I think that's it. I don't see any further questions. I hope we have answered your questions. So then I will say thank you so much for joining us again. We appreciate it. Please email us should you require a recording of this webinar. Also, this will be available on our YouTube channel by the end of this week, latest Monday. And we encourage you to visit our website or to get in touch with the relevant branch should you require more information. Please stay online to complete the poll. There are just 3 questions, and we do appreciate your input. And it will take approximately 15 seconds per poll, per question to be answered, or I will give you 15 seconds. So with that, thank you so much from all of us, and have a great day further.